Graphing inverse trig functions. Now, we looked at the three basic ones last time, but it may not be the basic one that they're going to ask us for. So say we had to do something like this. Y is 5 times the inverse sine of x on 3. Got to work out its domain and range. So the way I think about it is, I know the domain of the angle is in between -1 and 1. Well, sorry, angle is the bad word, isn't it? Because it's not the angle, it's the ratio, this one. So the domain of x on 3. So if x on 3 is in between -1 and 1, x must be between -3 and 3. Now the range, I know, is from -pi on 2 to pi on 2. But remember, you group it with the y. So that 5, we bring it over here. It becomes y divided by 5. So y divided by 5 is in between -pi on 2 and pi on 2. So we get -5 pi on 2 and 5 pi on 2. Now when it comes to drawing it, you can draw the same graph for everything. All I'm going to do is change the numbers. If you're only drawing one on there, I'll get my template, which has got the sine curve on, and I'll just mark off, instead of 1 and -1, I'll mark off 3 and -3, and instead of pi on 2 and -pi on 2, I'll mark off that. Bingo. Got my graph. So as long as they're only asking for 1 on there, I'm fine. Let's have a look at this one. Inverse tan of the square root of 3 minus x squared. Now the domain for tan, or inverse tan, is all real x. However, in this case, I got a square root, which is going to put some restrictions on that all real x. Because I still have to satisfy the domain of root 3 minus x squared, because that's what I'm substituting into. So 3 minus x squared has to be greater than or equal to 0. So I actually could only substitute numbers in between minus root 3 and root 3 for this one. Now, because there's a restriction on the domain, well, I have a look what happens with the range now. So when x equals root 3, we're at 0. Minus root 3, we're also at 0. That makes sense, because it's going to be an even function because of the x squared there. So let's have a look in the middle. So at x equals 0, we get pi on 3. So my range is in between 0 and pi on 3. Okay. It's something like that. Something like that. Strange looking graph. Looks a bit like a semicircle, doesn't it? The inverse sine of sine x. Very tempting just to draw the line y equals x. But we've got to consider our domain and range here. So the domain is normally in between -1 and 1. So we're going to say sine x is in between -1 and 1. Well, when is sine x in between -1 and 1? Well, it always is, yeah. So the domain will still be all real x. The range, however, will change, because it's the range of an inverse sine function. So my range will be between -pi on 2 and pi on 2. So what's this going to do to the graph? We know it's got to look something like y equals x. So fair enough, there's y equals x in the range that I want, but this curve's got a domain of all real x. So what does it do? I guess it's got to stay like that. It's either going to zigzag, or we might have parallel lines or something like that. So I guess we just test some points. And when we do, we find out that actually, yeah, this one zigzags. Zigzags. As opposed to the other way round. So if you had to find the sine of the inverse sine of x, okay, well normally my domain for the sine curve is all real x. However, there's a restriction because I'm substituting into the inverse sine of x. So it will take on the domain of inverse sine x. Well, I've now restricted the domain, so what's going to happen to my range? If I substitute x equals 1 in, I end up with 1. Minus 1 in, I get -1. This kind of makes sense because again, you're expecting y equals x. Have a look at the middle. Yeah, sure enough, 0 equals 0. So for this one, when we draw it, and it'll just be between -1 and 1, but it'll be that piece of the line, y equals x. Okay, so that one would be just a piece of it. Okay. So 1C, just drawing up different inverse trig graphs.